This is blown into glass tube. And the people down in front can see there's, although this is mostly gas, there's a little bit of liquid in the bottom of there. Okay? And you guys are working through equilibrium problems, and the general equilibrium constants were written this way for a simple bimolecular reaction where reagents A plus B yields products C plus D. Now usually, in most of the things you're going to do this year and even next year, you're going to have either heat or a catalyst here to go this way. But I know yesterday Dr. Madison showed you that occasionally some reactions are not driven by heat and catalysis per se, but are driven by entropy. In other words, they can take heat from the surroundings of the room and proceed. And that's what you're going to see here. Because we're going to, if we call these molecules of nitrogen dioxide, which is produced from engines at high temperatures, because nitrogen doesn't generally get involved in combustion at low temperatures, the temperatures at which natural gas or gasoline or oil generally burn, or coal. But at high temperatures, and of course in electrical coal generators, and in some diesel trucks and high performance engines, we get a lot of this NO2. And NO2 plus O3, ozone, plus PAN, which is peroxyacetyl-nitrate. These are some combustion products that result from high temperature engines. And of course, since in the United States and in much of the world, about 80% of the electrical energy is one way or another produced by fossil fuels, we get a lot of this. And in places like Los Angeles, which is a natural basin and really a desert, or if you just have enough cars and electrical plants and combustion sources in a large city, dense population, you'll get this. Now, about 40 or 50 years ago, smog in Los Angeles was so bad that the state of California, before EPA was even founded, started passing laws that required NO2, required catalysts to be put on cars in California. Later on, the rest of the company followed on, and now we have NO2. We have catalytic scrubbers on the tail section of almost all American automobiles. Okay, so what's the reaction here? Well, we showed, at least the people down front, there's a little bit of liquid in this. This is a bigger gas tube of NO2. This will be our reference tube, and you don't see that liquid. But in any molecule like this, if it can undergo a reaction, there's always a little bit of the product left, product that's available. And that concept is called microscopic reversibility. So it can always, there's always a little bit of this. If NO2 can combine with other NO2 molecules in a confined space and produce N2O4, we call that a dimer. We would call this a monomer and this dimer. And maybe from high school you remember a little bit of organic. For those of you taking organic, we'll see it again next year. But here we're going to see it form in a different way. For example, to try to produce more product or more reagents, there are a variety of ways you can go. One is to add heat, which is what we do to most of the chemical reactions that you see that you're going to do for the next couple of years and beyond. And you'll notice right away, this goes from just a nice, sort of a light amber brown to a much darker brown black. Means that it's pushing this actually back this way to more reagent, because this is really a single. This is more like A yields C instead of two different reactants. Okay, so you notice that's getting brown black. Now, in this one, this is called the dry ice alcohol, dry ice acetone bath. And you notice the room temperature here is 21 degrees C. And if you go on, maybe next year in organic, but certainly sometime, if you go on to do much science, especially chemical synthesis, probably have to make a dry ice acetone bath. And the reason you make these is when you want to uniformly cool something down to cryogenic temperatures, you can't just take pieces of dry ice like this and put it on the side, because you don't get even distribution of the temperature. It doesn't do much, especially in there, because the dry ice sublimates, turns from a solid to a gas. But if you dissolve the dry ice in alcohol or some other organic solvent like this, then you get a nice continuous media. And you notice right now this is down to minus 72 degrees Celsius, which is just about the STP of dry ice, or when CO2 becomes a solid, or when it sublimates from a solid to become a gas. It doesn't go through a liquid phase. But anyway, this is minus 78 degrees, or roughly minus 100, 105, 106 degrees Fahrenheit. So we have a nice bath of very cold cryogenic temperatures that you would only see at the North or South Pole ordinarily outside of something like this. You notice as soon as I put this NO2 tube in, we no longer see this nice brown NO2 color, and we certainly don't see this dark brown black, which suggests that more NO2 is being concentrated in that tube. Instead, we see a blue-white isotope, that all the color is gone. And in this case, instead of heating up atoms or molecules to make them to collide and react, in this case, we take away energy, in which case, in a confined container like this, they bump into each other and they form the dimer, N2O4. Okay, so this is considered to be a thermal equilibrium. So the conditions of the container, the temperature, etc., can move this arrow one way or another. And in this case, when we take away temperature, since it's an entropic, then we take this NO2 and make the dimer N2O4 by dropping the temperature. Okay? When we heat the temperature up to 100 degrees, boiling water, which is our boiling water bath, we get more of the original NO2. So that's the thermal equilibrium of NO2, and it's the most visible, simplest one I think we can show you. Now, you can do these things without temperature equilibrium, concentration equilibrium. You can either take away products to push the reaction this way, or increase this to push the reaction, increase the concentration of products to push it back in the direction of reactants. That would be concentration or reagent equilibrium. Any question?